I'm really honored to for this opportunity here to present in this Laserlab-Europe seminar here online. And I'm very happy to see many participants joining today. I will be speaking about multipass cells, as announced already. And yeah, I call them basically quasi-guiding systems, which we use for post-compression and nonlinear optics, as you will see in the presentation today. Let me start, but before jumping into the topic, a very quick intro. My group is the group of ultrafast photonics research and innovation, a group hosted both at DESY, mainly at DESY, but also at Helmholtz Institute Jena in Germany, both institutes in Germany. And we have a focus here on current research topics, namely addressing really quasi-guided nonlinear optics, in particular in multipass cells, then ultrafast laser developments, mainly for secondary photon and particle sources. And yeah, a new topic, which is not part of this talk today, gas phase sonophotonics. I will briefly mention it at the outlook of this presentation. The work presented today is was carried out by my group, and also in very close collaboration with the DESY Laser Science and Technology Group. Many of the works here have been jointly conducted. Yeah, let me start then to jump here right into the topic with a short motivation. Ultrafast lasers, if we look at ultrafast laser technology, there are in particular two very important sources. The titanium sapphire laser, a laser which provides ultra-short laser pulses, but at very limited average power. On the other hand, we have terbium laser systems providing very high average power, reaching up into the kilowatt regime, but the pulse duration is rather limited to not very short durations. We're speaking about hundreds of femtoseconds here. If we look a bit, and of course there is OPCPA technologies available as well, and a couple of more systems. If we look a bit back, there has been a prediction in, I think this paper came out in 2014, that OPCPAs would mature to much higher average powers and be developed further in this direction. This has certainly happened, and there have been great achievement over the last couple of years in this direction. But I would say nowadays, there is another very attractive approach, and this is the approach I will be discussing in this presentation, among other things today. And namely the approach just taking the terbium system and directly post-compressing such systems by utilizing very large compression factors and efficient compression schemes. And in particular, this combination of very efficient compression and large compression factors has been really receiving a boost over the last couple of years by this multipass post-compression technology, which we review in this recent review published in Optica. Yeah, let me move on and move over to a very short intro into what is a multipass cell. I suppose many of you probably know this technology, but a short review here is needed. Imagine we have two mirrors, two concave mirrors typically facing each other, and we have an ultra-short laser pulse bouncing many times back and forth between these mirrors. We can now introduce a nonlinear medium between these two mirrors, such as a gas or a solid plate medium, a glass plate, for example. And in this nonlinear medium, the laser pulse can undergo self-phase modulation, thereby spectrally broadening its spectral content. And afterwards, we can post-compress this laser pulse using a compressor. This principle has been widely applied now to various laser systems, but in particular to the terbium laser platform. Very importantly here is, particularly when we speak about terbium lasers and large compression factors, but in general for post-compression, it is important to consider that we, while gaining large nonlinear phases, large B integrals, we need to find a way to mitigate, to avoid the beam to collapse spatially. This is done, for example, traditionally by utilizing guiding structures such as fibers. And here, in this particular case, we use this quasi-guiding scheme, the multipass cell, which actually has similar properties. I will explain them a bit later why this is the case. Key features of such multipass cells have been shown to be very high power compatibility, large compression factors, which are supported very high efficiencies. They support excellent beam qualities. They are adaptable to very large parameter ranges. And maybe most interestingly, at least depending on the application, they really feature advanced amplitude and phase control options. Again, I will come back also to that topic later in my presentation. If we look at parameters, I'm showing you here an overview published in our recent review paper. And in this overview, you see essentially in red dots here, multipass cells, and in blue dots, other post-compression schemes. And we show here very clearly that in particular, if we look at high peak power and high average power, sorry, it was too quick, the red dots perform pretty nicely. Same for power efficiency, for the efficiency of the system, and for compression ratios. We can see that these systems reach, despite reaching very large compression factors, even still very high efficiencies, exceeding even 90%. And this is, of course, very attractive parameters. That has attracted many researchers and has really led to a spread of this technology in the ultrafast laser community. To illustrate this, and without being here too global, I focus here just on our institute, DESY, in Hamburg, in Germany. And here we see a map of the DESY campus in which I mark laboratories which host ultrafast laser systems. And I'm adding now basically to this map, which is a few years old already, more recent developments which have happened over the last 3 years, in which I indicate here in yellow, basically multipass systems that have been installed or that are currently under development. And while presenting this, I'm already seeing that there are labs missing because this slide is already half a year old. So I need to update that. Yeah, but it really, what I want to show here, it really shows the progress on ultrafast laser technology using this multipass cell option. And it shows it here on DESY campus, but I think this is an example for a trend that we see in the ultrafast laser community worldwide. Yeah, what I'm showing you is not only works, not only labs, of course, by my group, but by many other groups contributing and groups with which we are also collaborating here on campus. And yeah, another indication here, if you count papers that contain the word multipass cell or that focus on this technology, even only looking at journal papers will reach very large counts over the last few years that have been published on this topic already. We also have been publishing quite a few things, and just briefly mention that here, and I will now basically in the next few slides show you some selected results from the results achieved on these topics over the last about 3 years. I will start with a quick intro into this nonlinear optical quasi-guiding systems and explain a bit some basic features and why they are very attractive. Not only for post-compression, my first topic here, namely post-compression, and then but also for the second topic here, namely multipass cell-based nonlinear optics. I will briefly show you first a few examples for post-compression systems which we are currently working on or have been working on recently, and then also 2 examples for general nonlinear optics performed in multipass cells. But let me start very basic here and look at the multipass cell as a very special system. Nonlinear optics is typically, if we look back into the history of nonlinear optics, is typically performed either in a free space geometry or in a waveguide. The waveguide features very large interaction lengths. It features, to some extent, amplitude and phase control via dispersion engineering, for example, and some limited high power, high energy compatibility, well, actually very limited here. Free space optics, on the other hand, feature only very short nonlinear interaction lengths due to diffraction limiting this. Spectral amplitude and phase control is not easily possible here, but of course, very high powers are feasible. The multipass cell, which is here represented as a sort of unfolded schemes of many lens of a lens array, essentially, is optically very similar to a multipass cell. This multipass cell here is featuring basically nice properties of both previous schemes, and therefore being very powerful. There's another way to see this. If you think about a basic nonlinear optical process, it can be cell phase modulation or another nonlinear optical process where a certain laser pulse enters a medium, and then another laser pulse is emitting the medium. If we have such a process, and now imagine we could divide this process into many slices. And we could now, after each slice, tune amplitude and phase within this process. That would be a very powerful means of controlling a nonlinear optical process. If we at the same time also can make sure that this process happens in a guiding geometry, well, that would be even better and would even give larger flexibility on tuning and optimizing this process. But I mean, what I'm explaining you is exactly what a multipass cell can do if we take into account dispersion engineering, and not only dispersion, but also amplitude engineering concepts that we can apply, for example, by a clever mirror design or other means, inserting filters or similar systems into the multipass cell. Yeah, so this is a short intro here why I believe that this system is really powerful and will lead to many more things than just cell phase modulation based processes in the future. And it can really provide a means to overcome efficiency limits, bandwidth limits, spatial beam quality limits, and many other limitations in nonlinear optical processes. Let me move on and jump right into a few examples on laser pulse post-compression. I'm starting with an example for lasers developed here for the free electron laser facility in Hamburg, Flash lasers that are being used as pump probe lasers. When we speak about free electron lasers, I have to introduce here that many experiments in such systems are being carried out in a pump probe fashion when optical laser pulse is being used in connection with a free electron laser pulse, an X-ray pulse, for example. And then a controlled delay leads to a pump probe scheme. Such lasers then, in particular, if you consider a large variety of different experiments that might be targeted at such facilities, such optical laser pulses need to be, or laser systems need to be highly efficient, highly reliable, easy, transportable across large experimental halls, and they need to allow great parameter flexibility. We have been here at DESY installing a couple of such systems now based on exactly a multipass cell concept, where we start with a picosecond laser, and then apply nonlinear spectral broadening in multipass cells. And after transporting the beam to a user end station where experiments are carried out, optional wavelength control schemes can be applied, and then the pulses are delivered to a user end station. Let me show you one example here, a very particular example where we have not used a standard multipass cell, but a very particular one, namely a multipass cell that is essentially a hybrid solution between a multiplate and a multipass spectral broadening scheme. Here we use more than 1 picosecond duration input pulses that we send into this multipass cell, spectrally broaden them by passing multiple glass plates placed inside one multipass cell, and then reaching larger and larger spectral broadening factors as we increase the energy. The multiple plates here are being used for increasing the maximum B integral that we can achieve per pass through the system, which is limited to small values if we have a single plate in the system only. And we have been reaching here particular work by my colleagues Marco Seidel and my former colleague Annelies Viotti. They have been reaching here very short pulse durations by employing actually a double multipass cell approach, a cascaded multipass cell approach, and where they went all the way from 1.2 picoseconds down into a sub 10 femtoseconds. A very similar system than the one I'm showing you here, and with similar results, but containing only a single stage, has been installed as a permanent laser and one of the free electron laser beam lines here at Flash in Hamburg. And this is an example of a system where you see that such multipass cells are not only good for proof of principle demonstrations, but for actual everyday operation, as the system has been operated almost 3 years already in a more or less 24/7 operation mode. And is not now being used as permanent facility laser here in Hamburg. Let me move on and switch topic from electron laser pump probe lasers, where we use this multipass cell scheme for post-compression, to another very attractive topic, also an important topic here at DESY in Hamburg, namely laser plasma acceleration. Laser plasma acceleration, without really going into any details here, is a process where essentially a plasma wave is being used for accelerating electrons over very short distances to very high energies, reaching easily into the mega electron volt or even giga electron volt energy range. and with the main feature that very compact accelerators can be built. The challenge, and a big challenge in the field, has been since long time that very intense lasers are required here, which typically run only at limited repetition rates. And this has been a bottleneck for really building application relevant laser plasma accelerators. There have been a few reports on using few cycle pulses for such laser plasma acceleration experiments. And now with the new technology that we have available for extreme post-compression, we are actually reaching a regime where we can think of using ytterbium systems, so really high average power lasers, convert them to very short pulse durations and use these systems for laser plasma acceleration. This is one of the topics we're also addressing here at the DESY, and which I want to briefly cover here in my talk. A few years back in 2020, we already showed that it is possible, yes, to compress into cascaded gas-filled multipass cells laser pulses from the picosecond regime down to the few cycle regime. At that point, this was a proof of principle demonstration that had reached only low efficiencies and sub-millijoule levels, very far from the terawatts we need, the terawatt range that we need for laser plasma acceleration. Meanwhile, a few other groups have nicely catched up here on this technology, and in particular the group of Jens Limpert in Jena and Oleg Tronin here also in Hamburg. They have reached very nice, demonstrated very nice systems, again using for each system two cascaded multipass cells. In one system here, reaching compression factors 29 at almost 1 millijoule at the output, but reaching the few cycle regime. And the second example down here, compression factor 33 at the microjoule level pulses, but also reaching very short pulse duration. So very promising examples that show the powerful, that illustrate this powerful technology. We have now aimed at boosting this compression factor further and at the same time pushing the energy in order to reach close to the terawatt regime, which is required for laser plasma acceleration. And this is what I'm going to show you in the next slide, where we basically aim at more than 100 compression factor while operating at multi-millijoule levels. You see a view here onto the system that we have currently under operation in our laboratory, and you will now see a few some data on what we have recorded so far. Before, a quick reminder, what are we utilizing here? We utilize two cascaded multipass cells, one filled with argon, one filled with neon, and both actually completely assembled using as key ingredient dielectric mirrors that provide very high efficiency for the entire post-compression process. Yeah, I'm also showing the key people involved in this experiment, and then a view into the second multipass cell. This is actually a real photograph of an operating few cycle multipass cell, illustrating that we are generating many colors in this cell. So sending in an invisible 1 micron laser, we convert this laser into a colorful broad spectrum. The key results that we have reached here, without going too much into details, essentially show compression from a picosecond about down to the few cycle regime. And to really see what is happening, we have to play a trick. We have to zoom into our plot here, both on the intensity scale and also on the time scale, and to make actually all the pulses visible. So in red here, you see the ingoing laser pulse, which is fairly not really visible on this plot, but you have seen now when scaled in how this pulse looks like initially. And then the pulse after the first compression cell is in blue, and the blue area, and then in the blue line is the few cycle pulse coming out after the second multipass cell following compression via dispersive mirrors. We're reaching 6 millijoule at sub 10 femtosecond with the system, and there were actually a peak power regime at reaching 0.3, about 0.3 terawatt, which is a regime which already should support mega electron volt laser plasma acceleration. I'm also showing you on a second plot here very similar data, but now recorded not using a FROG, frequency resolved optical gating, as used for the first plot, but using a third order autocorrelator to investigate the temporal pulse contrast of such a post-compressed pulse. And you see here in blue the pulse coming out of the laser. Truly speaking, not a very high contrast, but this laser system has actually never been optimized for extremely high contrast, temporal contrast. And then you see the output of the first multipass cell and the output beyond the second multipass cell. And we clearly see that temporal contrast, if we normalize it to essentially, if we normalize this data here to the peak of the main laser pulse, the temporal contrast is increasing over a large range, which is expected as the peak power is increasing at each compression stage. But this is, and clearly I'm showing here large scales on the picosecond range. This data is not resolving the weak pre and post pulses, which you see in the linear scale here, which are of course present when we post compress pulses. Let me move on. Maybe a quick summary here. We have here demonstrated really multi-millijoule class terbium laser pulse compression by more than a factor of 100, approaching the terawatt peak power regime, and at the same time demonstrated temporal pulse contrast improvement. A few words here on energy scaling. Very interesting topic is for further boosting this up in peak power energy scaling. And here we face the limitation that multipass cells are typically limited in length and laboratories as well. And we can show, it has been shown, for example, in the paper displayed down here, that the system length, if we scale standard multipass cell system in length, supports linearly with increasing length more and more pulse energy, limited essentially by effects like laser-induced damage threshold of the mirror as the main effect, and maybe ionization as a secondary effect. And this is a very linear scaling. Actually, sorry, this is the other paper. This is a paper which describes already a few years back from my postdoc time, which describes linear scaling in gas phase nonlinear optics. And this can be very well applied for this scheme here. The question is now, how can we go beyond this linear scaling regime? You end up with very large systems. This is a big problem here, as for example, with this system here that is shown from Trump Scientific, where more than 10 meter long MPC was used to compress more than 200 millijoule laser pulses. This is a very, very impressive number, but the system is really large and therefore not very practical. So alternative scaling approaches are really needed. There have been a couple of papers discussing them, and I don't have the time here to go through all of the approaches that have been proposed so far. I want to quickly summarize one approach, which is an approach which we have been looking into. This is an approach which considers multipass cells which are not just made out of two mirrors, but which are using more mirrors. So we're considering here, for example, a so-called bow tie geometry. And the bow tie geometry is essentially a geometry where we use at least 4 mirrors. And in this 4-mirror configuration, we can consider that the beam path from focusing mirror 1 to focusing mirror 2 is not the same as the returning beam path from mirror 2 to mirror 1, as typically the case for standard multipass cells. If we have these two non-identical paths that exist in such a multipass cell, we can plot a stability diagram for a multipass cell, and we see actually large regimes appearing in this stability diagram. So you see here on the diagonal line, this is basically the normalized length of length 1 and length 2. And you see on the diagonal line where L1 is equal to L2, the standard multipass cell configurations and the stability range reaching here from 0 to the maximum length of the standard multipass cell configuration. But we can now go outside the same standard regime and really explore different regimes for multipass cell post compression. And interestingly, there are regimes which support much higher energies on the same footprint. In particular, if we employ folding geometries, and we can use that if we make sure that the laser beams are not just tightly focused between the mirrors, but if we utilize sections in the multipass cell which are close to collimated. Illustration here again of the corresponding lens arrays of these two regimes. Without going more into details here, I want to briefly mention that we are working on this topic Obviously, we have been publishing a theoretical proposal paper here, and we also have done experimental tests by now. I'm showing you here some preliminary data, actually not the best data, as I just learned from the student Arthur Schoenberg, who's working on that topic. There's already better data available, but you get to see the preliminary data, and which will be hopefully published very soon, of a very compact multipass cell of only 40 centimeter length, supporting 8 millijoules, which is quite a nice achievement. And in particular, it is a very nice achievement because we use here a multi-mirror geometry, which exhibits energy scaling options which go beyond the standard linear scaling of length versus energy, and therefore really put nice hopes up here for high energy multi-pulse post-compression systems in the future. Okay, since time is really moving fast, I need to advance here to the second topic, namely leaving post-compression and moving over to multipass cell-based nonlinear optics. I'm going back to my initial scheme, illustrating the beauty that we have if we use a multipass cell and combine it with dispersion engineering. And one very nice work that has been appeared just very recently published by the group of Oleg Voronin actually uses such a multipass cell for not cell phase modulation, but for second harmonic generation. And very interestingly, using clever dispersion engineering tricks, you can the Voronin group here has shown that it is possible to efficiently convert a laser beam into its second harmonic in a geometry where actually a single pass through the crystal is not even necessarily phase matched. So you can use quasi-phase matching tricks to boost the efficiency of our harmonic generation process. Here, this was done in a proof of principle scheme for very long laser pulses, where the actual efficiency record reached was, I think you see the data here around 60 to 70%, but which is maybe not surpassing, if I'm not wrong here, the typical values one can even reach for narrow bandwidth lasers in a single pass geometry. But this is not the main point of the paper. The main point of the paper really is you can use clever dispersion engineering and boost non-phase matched geometries, thereby having a quasi-phase matching geometry for essentially a free space or quasi-guided optical arrangement. This really puts up hope for many more frequency conversion schemes that can be exploited via interesting dispersion engineering. Let me conclude this topic here by mentioning that we're also working on exactly this topic, and we are at the moment really carrying out research on dispersion tuning in very broad bandwidth second harmonic generation multipass cells. You see some very preliminary data, which I don't want to comment any further, but I can tell you already we have very promising results here that show that dispersion engineering really can play a big role for second harmonic generation processes and respectively other processes as well. That's, by the way, one paper also published by us and co-workers and by the group of Francesca Caligari on dispersion engineering in multipass cells, not for second harmonic generation, but for post-compression. Okay, now another topic beyond simply post-compression that I want to discuss here briefly, which is going from second harmonic generation over to back to cell phase modulation, but not cell phase modulation for spectral broadening, but for something else. If we look at the spectral broadening process, we typically get a symmetric spectrum because the laser pulse that we use for spectral broadening is symmetric in time, therefore mapping out a symmetric spectrally broadened frequency. If we use laser pulses which are not symmetric in time, and this could be in extreme cases a triangular or sawtooth shaped laser pulse, then we should also get a very asymmetric spectral broadening process. This is the case, and we have shown that this is possible. A very important ingredient here is, again, dispersion engineering. Especially if we use shaped laser pulses, we have to make sure and want to use a dedicated shape to control a process in a certain way. We need to make sure that the laser pulse keeps its temporal shape throughout the generation, throughout the passes, the many passes through the multipass cell, and this can be done at least to some extent if we use a dispersion balanced multipass cell. This is what we have been setting up using a home-built ytterbium laser system, which a CPA laser system, shown here on the top row, which we then have complemented with a pulse shaper that we use for shaping this triangular or this sawtooth-shaped laser pulse. And then we have also complemented the system by a multipass cell after the CPA units, then a spectral filter and a compressor behind. If we do this, we can actually start to tune the output spectrum of such a laser system. This is illustrated here. So essentially, we use a pulse shaper, send the laser pulse into a multipass system, and then after applying a filter, we can get a spectral filter. We can get a laser pulse out, which is centered at a different central frequency. You see the measured experimental data here with the input spectrum shown in red and the green output spectrum before and after filtering, as well as the corresponding measured temporal pulse structures. We can, by flipping the phase, we can shift the spectrum or shift the tuning from one side, from one spectral direction to the other spectral direction, and really play with the output spectral central wavelength. And this is really a feature which allows to build ultrafast laser systems which are not just emitting pulses at the central frequency, the central wavelengths of the supported by the gain medium, but really we can effectively get pulses generated outside the gain medium of the bandwidth of the gain medium. Yeah, maybe a few more words on this before I'm already coming to the end of my talk. We have been inspired by earlier works by, again, the group of Jens Limpert in Jena, who have looked at a similar process, but actually used the standard spectral broadening system, then applied spectral filtering and looked at the temporal contrast of basically one side loop of this spectrum, this broadened spectrum. By doing so, they have identified that such an output pulse after spectral filtering here features extremely nice temporal contrast characteristics. Inspired by this work and knowing that pulses that have undergone nonlinear processes and basically then pulses that exist only of frequency components which were generated in the nonlinear process, such pulses can really feature very nice temporal pulse contrast. We have looked exactly into this. We have set up a third order autocorrelator for, in this case, about 1 microjoule laser pulses. And we have shown, as you can see in this plot here, that you compare the ingoing, the laser pulse emitted by the laser in red and the temporal contrast of that one, and then in blue, the temporal contrast of the spectrally shifted laser pulse. In this case, you see a large contrast improvement, although our measurement is actually limited by the dynamic range of the autocorrelator, so likely the range is even much larger than what we can display here. Yeah, so we can really use such a feature here, not only for such a method, not only for spectral shifting, but also for temporal contrast enhancement, and really see great potential here for high field science experiments. In particular, very, very high intensities are used, and where the temporal contrast is a very important quantity, such as, for example, for laser plasma acceleration, where this parameter is a very important one. Yeah, maybe last topic also on this experiment here, we have not only explored the temporal contrast, but also looked at the coherence properties of such an asymmetrically shifted laser pulse. And by that, without really going into details, you are welcome to have a look into our paper published in Nature Photonics early this year. And we have basically used our laser system, which is a frequency complex system, locked this system to a stable CW laser as a reference source, and then looked at the coherence by beating the CW laser with the frequency shifted output, and also beating the CW laser in comparison with the nonlinearly amplified portion of the oscillator of the system. And by doing such an experiment, we have actually characterized the phase noise of both the oscillator effectively and the output after frequency shifting. And the comparison shows that there is only very little additional phase noise generated in the shifting process, such that we can make the claim here that this shifting process is at least sufficiently coherent to support Hertz level coherence measurements. Yeah, this is the schematic here. Also, at here one picture of the real experiment showing that there's actually heavy and complex electronics involved into setting up such an experiment, which was mostly carried out by Saper Salman, my former PhD student who's now graduated. Okay, this already brings me to my almost last slide of my talk here with a short summary. I have introduced you opportunities with nonlinear quasi-guiding systems, or in other words, with multipass cells, speaking mostly about post-compression, and then also speaking about general nonlinear optics approaches that we can drive using multipass cell or nonlinear quasi-guiding geometries. As a short outlook here, yeah, our works go in multiple directions, but including pushing towards higher peak powers, towards reaching into the terawatt peak power regime, and pushing further towards even shorter pulse duration. At the same time, scaling up the pulse energy, a very important scenario for high energy lasers where multipass cells could prospectively in the future also play an important role. And then last but not least, a very important topic in my opinion, explore other nonlinear processes which can heavily benefit from the properties that multipass cells provide. I'm showing you here on the right side a little simple illustration here of how I see the field of multipass cells at the moment, but we have exploited quite a bit already, namely post-compression, some wavelength tuning, a few more topics like second harmonic generation, which should be above the water level, which is just below the water level. I have to update this plot as well. And but there's many more processes such as four-wave mixing has been a bit explored already, but not much. Parametric processes, terahertz generation, beam pulse cleaning approaches whatsoever. There can be many more things that we can utilize, that we can explore using this quasi-guided nonlinear optics approaches. And of course, all being useful for various applications in nonlinear optics, which I don't for various applications of ultrafast lasers, which I don't go into detail here in this talk. Yeah, again, a quick reference here to our review paper or perspective paper. Also, in terms of outlook, we are lining out further directions in this paper. That brings me to my last slide, and I think I'm just in time now, almost. And yeah, I would like really to thank everyone who has been involved in the works presented. I showed you already the people involved in my first slide, and of course the funding agencies. Let me conclude here by naming that we are doing other things than multipass cells as well, and I'm pointing you towards a very recent publication where we explore what we call a gas phase nonlinear optics, or gas phase sonophotonics, a new topic where we try to control laser pulses, laser beams, contact-free directly in gases. A very exciting topic which opens many new directions. And last but not least, position openings in my group. We have several positions opened by a new project which is going to be started early next year, the Mega EUV project, a project where we aim at a very high powerful laser source, which then drives an EUV source for imaging applications. And we are here searching for postdocs and PhD students with various topics covering multipass cell development, parametric amplification, high harmonic generation, and a few more. There's also a second project where we are searching for a postdoc or PhD student, and that is involving optical fibers to work with millijoule class laser pulses. With that, let me thank you for your attention.